4 of the GRE Math Subject Test Practice Test. So let's look at question 1 first. The function f over g can be extended to a continuous function in a neighborhood of 0. Notice how it doesn't say at 0, because if it said at 0, all 3 of these would be untrue. Well, that's technically an opposite, but in a neighborhood of 0 means only everything around 0 to a certain extent, like everything from positive epsilon to negative epsilon without 0 given some positive number epsilon. So to write it more precisely, okay, so that's what condition 1 essentially means. So is it true? In fact, yes. If you have a continuous and differentiable function and divide it by another continuous and differentiable function, then it is indeed going to be continuous in a neighborhood of 0. And of course, the proof of this is actually pretty long, so we're just going to leave it. Maybe I should. Okay, let's examine this using the definition of continuity. Continuity means that the limit as x approaches h of f of x is equal to f of h for all h in our interval. So let's try this. We need to prove that this is equal to this. But I mean, the funny thing is that limits satisfy this rule. And we are told in the problem statement that f and g are continuous. So that means that all we get is f of h over g of h by continuity, which is exactly what we need. Waste your time, then you can do this. Let's think about 2, which is the most difficult one. The function f squared minus f over 2g minus g cubed can be extended to a continuous function in a neighborhood of 0. Now this is also quite difficult. I mean, we're trying to prove that the limit as x approaches h of f of x squared minus f of x over 2g of x minus g of x cubed is equal to f of h squared minus f of h divided by 2g of h minus g of x cubed. Now, of course, a first approach we can take here is to just factor out f of x over g of x. And we're then left with what? F of x minus 1 over 2 minus g of x squared. And by the same exact rules, if f of x is continuous, well, f of x is continuous, and if g of x is continuous, g of x squared has to be continuous. So we can apply the same rules again, or, wait a moment. Oh. If we take the derivative here, using L'Hopital's rule, we get the limit as x approaches h of f prime of x divided by, what's this? Well, when you take the derivative of negative g of x squared, we will have to end up using the chain rule to write negative 2g of x multiplied by g prime of x. So you end up factoring this out into minus 1 over 2 g of x multiplied by f of x over z prime of x. Do we know that z of x is continuous around do we know that 1 over g of x is continuous around 0? Yes, because g of x is continuous around 0. Do we know f of x is continuous around 0? Well, of course. Do we know g prime of x is continuous around 0? We know that it's continuously differentiable, so yes. There we go. But then, the last one, number 3, is a bit tricky. The function f over g can be extended to a differentiable function in the neighborhood of 0. Now, here's the thing. It does say that g prime of 0 cannot be equal to 0, which prevents poles, causing it to be differentiable around 0, right? But it didn't say it has to diverge this way. You do also know that the limit as x approaches infinity of sine of x doesn't exist. But the function sine of x is totally bounded between 1 and negative 1. It doesn't diverge, well, it does technically. But at infinity, it will keep oscillating at the same rate between 0 and 1, meaning between negative 1 and 1, meaning it'll never reach a final value. If you say it converges to some number, if you say the limit as x approaches infinity of sine of x is equal to, say, I don't know, 0.5, well, I can just all I can do is, I can take some sine of x past a certain limit, and in fact there are infinitely many instances of sine of x that fall outside a certain, okay, I'm saying gibberish right now. Essentially, if we say that sine of x, I don't know, approaches this limit right over here, what we can say is that for a certain epsilon, for some certain positive epsilon, there are infinite instances of sine of x of the range of. So, in other words, sine of x never converges as x approaches infinity. But that's infinity. We're talking about 0. So what do we have to do? Just invert x. The limit as x approaches 0 of sine of 1 over x does almost the exact same thing. And you'll come to see that sine of 1 over x behaves pretty weirdly as you approach 0. It doesn't have any known value. And of course, technically, you can substitute sine. The limit doesn't exist itself. And you can fill in the hole with g of 0 is equal to 0, but that doesn't really change anything about the nature of the function. Specifically, if you take the derivative, or just look at the graph itself, you'll see that the derivative starts rapidly changing as well as the function itself. So, that means that, well, you can take the derivative yourself, and via the chain rule, you get this, which means that as x approaches 0, this is going to spiral off to infinity, and this is going to keep oscillating between 1 and negative 1, which means it's just going to keep growing faster and going closer to infinity over and over and over. So, it's going to look something like this. So, that means that as x approaches infinity, this function is totally going to go, as x approaches 0, this function is going to go bonkers. And so, what we can do to actually restrict this to 0, because it has no known value of 0, is let g of x be x squared sine of 1 over x. What does that do for us, you might ask? sine of 1 over x is still bounded between 1 and negative 1, which means that this is always less than x squared and greater than negative x squared. But as x approaches 0, this approaches 0, and as x approaches 0, this approaches 0. So this is squeezed into the middle, and thus the limit as g of x approaches 0 is 0, right? But the derivative doesn't change. In fact, it gets worse as x approaches 0. Now, all you need to do is just let f of x be something simple, like, I don't know, x. Now, what we have is g prime of x is definitely not equal to 0 at 0, but g of x is equal to 0 at 0, and f of x is equal to 0 at 0. Which means that if we divide them, or in fact, we should actually switch them around. If we divide one by the other, we get x sine of 1 over x. Does that look good? Oh, no, it doesn't. It looks something like, if I remember correctly, which means that at 0, it's not exactly differentiable, to say the least. So, I mean, you can take the derivative yourself to find out if it's continuous or approaches a limit at all. If you take the limit, you get sine of 1 over x, plus, if you take the derivative, x multiplied by negative 1 over x squared, cosine of 1 over x. So in other words, you get a sine of 1 over x minus 1 over x cosine 1 over x. Great, so we've got something that's indeterminate as you approach 0, something that's indeterminate as you approach 0, and something that approaches infinity as you approach 0. Which means that the derivative is totally screwed up. So that means that 3 is incorrect, and our answer is 1 and 2 only. Finally, let's move to 60.